Welcome everyone to the next IITE seminar. It is my very, very great pleasure today to welcome Jacopo Grilli. We go back quite a while with Jacopo. We were postdocs together in Chicago, 10 years ago now. We were getting old. Anyway, it was great to be there because not only did I learn a lot from Stefano Alesina while I was there, I learned a lot from Jacopo himself. Technically, we were peers, but this is how it goes. So I'm very, very happy to have him here, and he's going to be talking to us about microbial communities today. And without further ado, please, Jacopo, take it away.
Thanks a lot, Gyuri, for the introduction. And I have to say that I also learned a lot from you. So this, for at least, like it's at least as much as you learned from me, if not more. And so today's talk, it's about a work that is not my most recent, let's say, but it's something that I keep debating with myself, whether it's something very deep or very trivial. So I thought it was a good occasion to discuss that with you. And it's really about some basics results on competitive communities. So before I start, just to spend a couple of words from where I come from, actually where I am. So I'm from Trieste, from the ICTP, which is a very special place. It's a UNESCO institute where we do research, but also have the mission of fostering science in the global south. And we have a lot of activities, seminars, schools that happen here or worldwide. So check out what we do. Mercedes is part of our scientific council and visiting every year. So you are more than welcome to get involved and visit us. So what I want to start is what is the standard setting of community ecology, which is, of course, the fact that it exists a community. And typically, the way we study community ecology is that we imagine that there is some regional pool of diversity, which sometimes we refer to as a meta-community. And in some sense, this local community that is what we're studying is coupled more or less tightly with this pool of diversity. And somehow this diversity is really, this meta-community is really represented as a pool of diversity. And so sort of, if you take like a very simple standard plain vanilla model of community, what like this generalized local water equation, what to describe is the dynamics of different populations. And these populations, these labels, 1 to capital S, are actually the species in the meta community. And what you all do since primary school is to calculate the long-term behavior by setting this derivative to 0. And what you discover is that some species, if this corresponds to a fixed point, have positive abundance and they coexist in these communities. And there are some species that in this attractor are actually equal to 0 and they are locally extinct. Now, this is something, as I said, it's sort of I guess, the bread and butter of the people connected today. And of course, a natural question is who is in this pool, right? And who is this in this pool is represented by what are these parameters. So these intrinsic growth rates R and these interaction matrices AAG. And sort of a natural choice that we do since the 70s is to, or even before, is when we want to describe a community, a natural way to do it is to assume that these parameters are somewhat random, drawn from some distribution. And this approach has many pros. So the first thing is that it leads to somewhat general universal prediction in the sense that actually many details don't matter where this distribution is taken from. For instance, what is the properties of this distribution? The only thing that matters are a few moments. And also these results are somewhat non-trivial, and at the same time, somewhat tractable, at least when we consider communities that are large enough and there are many species. Now, this is not just, of course, something that we can do using local thermodynamics, and we can extend it to a consumer resource model, which is actually sort of what I described. Now, this might be, this kind of model might be slightly different from the version you're used to, but and is more suitable for microbial population, where you imagine that, I mean, it's what is typically used for microbial population, where you imagine that there are some resources, here represented by the variable C, and these resources are sort of entering the system with some fixed flux, and then they are consumed by species, and species grows out of these resources, and then they can. And so in this case, the pool, sort of, if we consider this system with many species and we assemble this system, what we consider are random consumer preferences in the pool. So again, the idea is we can imagine that we assemble this community from some meta community, and what typically is done, or often is done, is to assume that these consumer preferences, which represents how much a given species consume a given resource, are taken at random. Now, the key assumption, and this is sort of, I mean, of course, this assumption of random interaction has a long history, and it has a long sort of series of I mean, it sparked like several discussions. And the key point of what I want to highlight here is that there are two key assumptions about choosing random preferences. And the two key assumptions is that somehow this composition of the pool is in some sense limiting. So for instance, it doesn't allow extreme strategies like a generalist that consume all the resources. And the other thing is that it's completely uninformative of what are the properties of the local community. So for instance, in the pool, all the resources are equivalently consumed in the pool, while in the local community they could arrive at different rates. Now, just to stress something that is important, the key point is that even if this community is assembled at random, the final result, so what you have in the local community, is highly non-random. Right? So the community that you have in the local communities are not like just resembling the properties of the pool, in the sense that they are not a random selection of species, but they reflect the input. But they are still constrained and limited by the diversity that is present in the pool. Okay. And so this is like a main point. So one question that we asked was, how do we remove these contingencies? So what happens if we don't, we consider competitive communities where there is no contingency? So basically where the pool is, if you want, the pool is expressive enough or can be explored enough such that all the possibilities are present. Now, this can be done, let's say, you can imagine on doing this in two extreme ways. One is to have a pool with all the possible consumer preferences. So, for instance, if you assume that a species can either consume or not consume a given resource, this corresponds to choose all the possible 2 to the r choices. So, for instance, here we have 2 resources in black, and there are 4 species representing all the possible combinations of consuming 1, consuming 0, or consuming both. An alternative is to imagine that actually we have some sort of eco-evolutionary dynamics where there are consumer preferences, and these preferences evolve in time. So there is a mutation, and these mutations appears with a very low frequency and then can grow or can go extinct. Now, one can do these two things or anything in between. And in the setting that I'll describe, these two alternatives are equivalent. They lead to the same result. So typically I'll describe the one on the left, so this sort of very large pool of diversity, but also sometimes I refer to the eco-evolutionary dynamics, and they give the same result. So basically, we are in a very, very simple setting where we consider a set of species and a set of resources. So the resources are these CJ, are labeled with the Latin letters. And we describe the dynamics, the joint dynamics of concentration of resources and populations. And the key players in these dynamics are the preferences. And for what I'll describe, these are all the possible combinations of consumer preference. So you have all the species that either consume or not consume a given resource. So if I have R resources, I'll have 2 to the R possible species. And then there are 2 other important parameters. So one is the dead term, and the other one is this delta alpha, and the other one is the maximum growth, eta alpha, which represents how fast these species grow, and the other one, how fast or rapidly they die. Now, of course, if we consider all the possible combinations and we don't specify any rule for this death and dilution, the outcome is pretty trivial. So what happens is that all the if there is no dependency, basically the outcome is that there is the monodominance of a generalist with the maximum possible growth and the minimum possible death. Okay. So now, if you want to have sort of an evolutionary algorithm, of course, you want an evolutionary dynamics. You need to impose, I mean, unless you are happy with this result, you need to impose some trade-off between these parameters. And so a natural way to impose this trade-off is to assume that there are sort of 2 extreme choices. One is a complete specialist, and on the other end, a full generalist. And somehow there is a cost in consuming a resource. So you can put this cost in mortality, or you can put this cost in growth. But basically, there are 2 extremes. So a specialist pays a minimal cost compared to the generalist in consuming these resources. So we have these 2 extremes where a specialist has an advantage when the resource is specialist is present, and the generalist when the generalist is able to grow in multiple combinations, but is less efficient. Okay, and this parameter chi represents the cost that is paid in consuming one resource. So the question that I want to ask is something that is sort of quite simple and quite standard, if you want, which is, suppose that I take this model and I consider this model with this shape of the trade-off, and then I consider a given resource input. So resources are provided with different rates, which is dependent on the resource. And I want to know if I look at different at this vector of resource inputs, what is the long time behavior of the population abundance? Okay, so standard question somehow. Now we can build on several works from the past, and basically in this simple setting there is a Lyapunov function, so there is a globally stable equilibrium, and when one writes that, it discovers that it's very convenient to express variables in terms of a total biomass and another variable which is basically quantifies what is the fraction of individuals able to grow on a given resource. So I refer to this variable as either trait occupancy or function. And it really represents what is the fraction of individuals that can grow on that resource. And then, of course, we have the input, which is this resource quality, which, if you want to be a little bit more fancy, you can imagine as the available energy from a given resource in an individual lifetime in absence of competition. So basically, is how much growth can a given resource sustain. Okay, so if we express the Lyapunov function in these forms, what we obtain is a globally stable equilibrium that we can characterize. And so the result is that it's actually very simple. So basically, these functional occurrences, so these trait occupancies, the fraction of individuals that are able to grow on a given resource, depends monotonically on the resource quality. And if the resource quality is larger than a given threshold, all the individuals consume that resource. And below that threshold, only a finite fraction of individuals consume that resource. And the bigger is the cost of consuming a resource, the fewer core resources there are. So the larger is the cost, basically, the more is convenient not to consume all the resources. And of course, in parallel, we have the total biomass, and the total biomass depends on the cost. The larger is the cost, the lower is the total biomass. And the larger is the average resource quality, the larger is the biomass. And so this is like pretty general, and it's a globally stable equilibrium. Now, in this setting, basically, how does a community look like? Basically, the community that is assembled is a community where there are some core resources that are consumed by all the species. So all the species that don't consume these core resources go extinct. And all the non-core resources, we see that all the possible combinations coexist. So for the non-core resources, all the possible combinations coexist with variable abundance. And what happens is, in fact, that the diversity that we see is exponential in the number of non-core resources. Now, obviously, as you expect, when you have more species than resources coexisting, it's because we fine-tune things, probably. And in this case, this is, in fact, a marginally stable equilibrium. And it's because we have this very tight trade-off. Okay, so this trade-off that is very tight implies that we can have more species, that we have some effective manifold on which we can move, and this is a marginally stable equilibrium, which translated into this matrix means that we can choose the abundances of the species such that the functional occurrences are the ones at steady state, but we have multiple choices on how to choose. And now, as you expect, when you have a marginally stable equilibrium, it's very easy to break it. And I don't have, oh, I forgot, sorry. There was a slide that is not showing up. But basically, the way you can break it is that you can add a small deviation from the trade-off. And if you add this small deviation, what happens is that you have a lot of extinctions. And what happens is that all these results are conserved. Sorry. These results are conserved. And the things that differs is that you have fewer species. And you have a number of species which is not 2 to the number of core resources, but is 1 plus the number of core resources, of non-core resources. So you have the same functional attractor, but you have just fewer species, and these fewer species are selected based on this deviation from the perfect trade-off. Okay. So now this is a very simple setting where you have just consumers competing for resources, and there is a Lyapunov function, everything is controlled. So what we try to do is something more complicated, and actually have a communities where these resources species compete on are not coming from outside, but are also produced internally. And so we have a much more complicated model, which is shown here just to show that it's much more complicated. But basically, just going very quick in the terms, we have populations, again, that have some maximum growth rate or some efficiency. and they consume resources that have different energy content, and there is a maximum intake rate, and then there is a resource preference between 0 and 1. There is a functional response representing how growth depends on the concentration of resources. There is a death or dilution rate, depending on the context. And then when a species consumes a resource, doesn't fully consume it, but also release it in the environment as form of another resource through some resource conversion matrix D. And then there is also an intrinsic resource dynamics in absence of populations. So we have a way more complicated models with many more parameters and many more details. And one particular feature of this model is that resources are not only coming from outside, but also are produced internally through this cross-feeding mechanism. And so in this case, mathematically, there is not anymore a globally stable equilibrium. And so what we can ask is, does the result that we found before still hold? And again, what we do in this context is that, again, we consider a pool of species where all the preferences are present, and then we assemble the community starting from there with the trade-off that we considered before. And so if we do, basically, we try to apply the same result as before, we obtain something that is very messy, where different points represent different cross-feeding matrices. But the result is actually more simple when one rewrites this somewhat effective resource quality, which take into account cross-feeding. So basically, if one takes into account that there is an effective resource input mediated by population, then one obtain the same result as before. This is what I anticipated before. What if this trade-off is not perfect? So one introduce small variation between different species where there is a trade-off, but then it's possible to have some deviations. Well, one finds something that is very similar to what observed before. So there is still a very strong signal of what we obtained earlier. And so, as I said, I anticipated before, in this case where there is this small variability, diversity drops. There are not anymore 2 to the number of non-core resources. There is a smaller number. Now, this is so basically what we observed so far is that in this model, which is like in both the simple version and the more complicated version with cross-feeding, we see that if we start from this infinite species pool where all the possible combination of resource preferences are present, we arrive always to this globally stable attractor, which is characterized just by 2 variables, which is fully determined by this cost, so the cost of consuming an additional resource, and a resource quality, how much biomass, how much energy a resource can produce. And then this final state is represented just by the total biomass and this resource preference, this functional composition, this trait occupancies, so this fraction of individuals able to consume a given resource. And one gets a prediction of the diversity, which is determined by basically how many resources are not consumed by all the individuals that are present. And so one gets this exact solution, which is valid actually for any choice of resource precedence. Doesn't need to be exactly equal to 0 or 1, as long as it's bounded. And it's fully obtained with these resource qualities. Now, what these results represents, basically in sort of more geometrical terms. So basically, these models, these consumer resource models, are characterized by manifold of solutions, which is fully determined by this functional composition, so the fraction of individuals able to consume a given resource. And so in absence of fitness differences, what happens is that depending on the initial condition, the dynamics drives the community to this manifold of solution. Now, the fact that this manifold of solution exists is not something that is trivial and an obvious consequence of the equation we started from. So you can play this game and you can start from the equations and write the dynamics for these functional traits. So you can ask, I try to describe the dynamics of the fraction of individuals able to consume resource I. And when you try to do that, you discover that these dynamics depends obviously on the fraction of individuals that are able to consume both I and J. And if you try to write the equation for the fraction of individuals consuming both I and J, depends on the ones consuming I, J, and K. So the dynamics actually, the way this dynamics develops in time depends on this, which species, how many individuals are able to consume both I and J, right? Because this is related to actually niche overlaps. But at the end, the dynamics arrives to a manifold which is independent of that. And so what happens if you add these small fitness differences? So you break this perfect equivalence or this very tight trade-off, is that you have this fast direction that drives the dynamics of the manifold, and then you slowly end up in one of the corner, which is determined by the realization of this parameter epsilon representing the deviation from the perfect trade-off. And so if you imagine to generate many different communities with different realization of this value of epsilon, so these small fitness differences, what you end up with is very variable species abundances, because the value of the species abundance very much depends on the realization of these deviations, while the functional abundances are very reproducible, okay, because they are independent of this realization. And you can do the same game where you imagine that these fitness differences, this deviation from this trade-off depends on time. And if you do that, what happens is that you have a fast direction, and then you sort of explore this manifold over time based on this noise. And what you get is you get a very non-trivial dynamics at the species level, where species come and go and change their abundance based on the realization of this noise, while these functional abundances, these trait abundances, are quite stable over time, because the dynamics is very much constrained on this manifold. Okay, so this is a very simple and seemingly robust picture. And so the last thing I want to describe is what happens if we now, in the same way as we consider this very large pool of species, we consider a very large pool of resources. So we consider a system where there are many resources, and then we assemble these communities for this extremely large pool, or we have these eco-evolutionary dynamics that assemble the pool. Now, in this case, basically, this is equivalent to say that this resource quality is some random variable, and one can obtain a simple relation between diversity and the total biomass using this model, which depends on what is the distribution of this resource quality, the cost, and the number of resources. And one can imagine that this is a sort of equation of state linking diversity and total biomass. And you can imagine of doing a simple transformation where you change some property of the system. So for instance, you can change this resource quality, you can change the number of resources. And the interesting thing is that this model gives different prediction depending on what is the kind of transformation. So for instance, if you you increase the variance of resource quality, but keeping the mean and the number constant, you increase the number of species and the number of individuals. If you increase the number of resources, adding them on top, you increase both the number of species and the number of individuals. If you increase the number of resources by keeping the total amount of energy fixed, you decrease the number of individuals, but while increasing diversity. So you get an inverse relation between number of species and number of individuals. And so basically, these results gives a very simple way to understand how these communities, in this limit where the pool was extremely large, change in terms of diversity and total biomass as function of what are the conditions. And in some sense, this is sort of going back to the point where I started about random interaction, is that this is a different regime in which to study this model. And basically, what I described now is the case where the number of species in the pool is way, way larger than the number of resources. And so the pool does not limit is not limiting the diversity in the community, and we can reach this manifold. The alternative case is the case where the number of species in the pool is on the order of the number of resources. And in that case, the community that we find, it's something where we see a big component of the limiting, the contingency that was present. And so in the right case, in the case on the right that I described, only the trait matters, and somewhat what is really essential to describe the community is the shape of the trade-off, which is something that here I assumed, but if this pool is very, very large, basically the only thing that matters is where and what are the trade-offs between different traits. On the other end, the case on the left, the problem is way more complicated because it's somewhat resembles a constrained optimization problem. So basically, the dynamics feel the presence of this manifold, tries to get closer, but is strongly constrained by the contingency of the traits that were originally present. Okay? So I'll conclude now and leave space for questions and discussion. There are sort of these two extreme regimes, with or without this contingency. And even in absence of contingency, there is a non-trivial phenomenology that we can treat, we can describe, and gives non-trivial relationship between, for instance, diversity and total biomass. And of course, this is very strongly dependent on what is the form of the trade-off, where does it come from. And what is interesting to me is that when we sort of put ourselves in this regime, what really emerged naturally as the right variable to describe this community is not anymore populations, but is something about functional or trait composition in this community. So I concluded that, thanking all the people that contributed either directly or indirectly to this work, and you for your attention. Thank you.
Thanks, Jacopo. Although Guri's still in the participants. Oh, you are there.
Hi. Off soon, so I think you should make it, but thank you.
Okay. All right. So has anyone got any questions? The easiest way is to raise your hand in the chat. So Axel, you're up first.
I thought Mercedes was first.
Oh.
Okay, anyway.
That was applause, I think.
Here's my question. Super interesting. It's totally different from what I expected the outcome to be, and from how I understand the systems. And one of the points where I thought the story would go completely different is that if you have living resources and living consumers, you get so-called apparent competition, where the living resources go extinct. and that would correspond in your equations corresponds to negative resource abundances. And so why doesn't that not happen why is that not a problem in your model? That would be my first question.
It doesn't. So basically, it's impossible. Given the equations, the resource concentration cannot become negative because you are. You are always. If
always
the
adding stuff
equal to zero, the derivative is always possible, right?
Yeah, maybe it's a slightly different structure, right? Because a living resource.
Yes. So the difference is that basically a living. So going back to the right slide. So sorry, I don't know why it's blocked. But basically, what happens is what is the dynamics in absence of the consumers, right? So if you take this more complicated model, which I hope you see, what differs is the form of this function h, I.
Yeah.
So for a living resource, this hi will be quadratic, right? Well, in my case, it's a constant or it's linear. So in that case, the final result, so the analytical result is different, but and it's more complicated to express, but the outcome is the same. So you still have these traits emerging as the right variable, if you want, and you still have this manifold, and you arrive to this manifold. Now, the form of this manifold, it's a more complicated form of, let's say, the intrinsic growth rate of the resources in that case, but it's still there. I hope this clarifies, meaning that I cannot express this fi star, so this fraction of individuals consuming that particular resource, as a simple form of the property of that resource, but you can still show that you arrive to that kind of solution. Does this answer?
The other thing I thought is if the conversion efficiency is not always the same, if there are variation in the efficiency in which consumers convert resources, then also the potential function property goes away.
Yes. So if this becomes very large, so if this epsilon becomes, so as function of how big this epsilon is, so how far, so you have this trade-off, right? And depending on how far you can go from this trade-off, so how loose this trade-off is, you start deviating from this manifold. That's true.
That's correspond conversion efficiency?
It's not, I'm not sure if I would call them, let's say you have a trade-off. So you need to, in this model, you need to impose a trade-off, meaning that being a generalist it corresponds to a cost.
Okay.
Now, the point is you can choose this trade-off to be very, very tight, meaning that two species with that consume the same number of resources have exactly the same efficiency, let's say. Or you can say this is not tight, but there is like some deviation, right? If this deviation becomes very large, then basically this deviation is what is going to dominate in the final assembly. If this deviation is present but not small, you still see the effect I described.
Okay. So there must be something else, because if I add lots of resources and lots of consumers to my model, which otherwise has a similar structure, most of them go extinct. So there must be something interesting happening, which is different.
No, so in the case of consumers, as I said, it's different in the sense that in that case you don't have a relation as simple as this one. You cannot really write these functional occurrences as a simple property of the resources. Let's say in your case, you have like resources which have an intrinsic growth rate and a carrying capacity. I cannot write the functional occurrences as a simple function of these two parameters. Okay.
Okay.
And so you can have these resources going to extinction, right? So that we'll have effectively a parameters that will be equal to 0. But this, the fact that you have this manifold is still true. Okay, so it's still correct that, yeah.
Thank you. So other people also will have questions, so I don't want to kind of monopolize. Thank you very much.
Thank you.
So if anyone has any questions, it's the react button down the bottom and click raise hand. But just while people are thinking for a moment, I thought I'd ask something a little bit broader really is, how do you think we could best tell which regime any given community is in? And do you have any kind of sense of being able to line this up with any data? Or, I mean, I presume it's your data is the main thing you're targeting with this.
That's a good question. I think it's from an observational point of view, I'm not sure. From an experimental point of view, if you can have communities in vitro, of course you can play with this pool, right? And what you expect in that case is that somehow there must be, if what I'm saying is correct, I mean, if there are these two regimes, there must be a regime where the properties of these communities are independent of the pool. Right? And they become independent of the pool size, for instance, the diversity in the pool, but also on really the identity of the pool considered.
How large a pool would you need to be able to test
I don't know.
if you were doing it? Is it
I wish I
threshold?
knew. No, I mean, it's really a question that it's very hard to answer, in the sense that it really depends on what is this trait space that actually matters, and it's very hard to know a priori, I feel.
Yeah.
And it's very hard to know a priori how the pool occupies this space. So I don't have, I wish I have like even half an answer.
Yeah. Jonas, you got a question?
Right. Thanks for a very interesting talk. So I sort of continuing a little bit on Chris's question. So you have these like two regimes, sort of contingent and non-contingent. And in your model, sort of the non-contingent one lines up with the eco-evo one, or the everything is everywhere, or whatever you want to call it. But obviously, like if you change the model a little bit to include, say, essential resources as well as substitutable ones, you're going to get contingency also in the eco-evo sort of half of the space. Like you could get several globally eco-evolutionarily stable attractors of the system, depending on the initial conditions. Even with this infinite species pool with all possible traits, you could get these contingency effects. So I wonder if you sort of how you're thinking about, is this like contingent, non-contingent, like something we should keep in mind as?
Yeah, I don't think it's, I mean, I agree with you in the sense that I don't think that this contingent, non-contingent case implies that that everything needs to be non-contingency if we increase enough the species pool. So I agree that there might be situations where this is not true, right? What I'm saying is, I think it's important to keep this distinction in mind. I mean, that in some sense, in many cases, what we care about is not what is our, let's say, input in our, it depends, right? But let's say many things I care about are questions not about what is the input of our pool. So what is the properties of the pool that we consider, but really what ecology selects in some sense, right? And then it's true, there might be situations where there are like different, let's say, different functional attractors or trait attractors that are like alternative, and I totally agree. What I'm saying is, I think, I mean, let's say, whenever we observe something, it's important to ask our, I mean, let's say, I started asking myself, to what extent is this is something that is a property of the pool versus a property of the environment. Because like describing the property of the pool, it's like it's describing an initial condition, right? So it's not really what we want to do. And in this respect, this is also why I started asking myself whether this is like trivial or non-trivial, also in this respect, right? But again, I agree with you that this is a particularly simple situations where there is like a unique manifold that is very well behaved, and you could have situations where actually the final state is very much more there are multiple attractors, let's say, also in this functional space. So, yeah.
Thanks.
Thanks. Are there any more questions for anybody?
Maybe a clarification, Jacopo. You said at some point for the equations of Fi, you had a comment in passing that Fij, Fijk, or what didn't matter.
Yes.
In the end. Yeah, I was a bit confused by that.
So this means that if you, there is, let's say, a trivial sense in which what I described here could be true, which is that if you if you have like your model, you write your dynamics, this dynamics depends just on what fraction of individuals consume a given resource. In reality, if you have a community, right, the dynamics of this community does not depend just on this fraction, because it's different to have a community where there are two specialists or there is one specialist and one generalist, right?
Yeah, I agree.
Even if in different proportions, even if in different proportions, such that the fraction of individuals consuming a given resource is the same. So the dynamics depends on the fact that there are populations or individuals, and these individuals reproduce, and these individuals have different strategies. So the dynamics depends on who does what, right?
Yeah.
And not, but the point is, even if that is true, one can show, and even if there is not a local function, one can show that the final state does not depend on that. So that the attractor is independent in presence of this trade-off. The attractor is independent of who does what. Right? Then the way you arrive to it, or the point you arrive to this attractor, if there is a perfect trade-off, depends on that, but the attractor does not. Which is a bit, yeah. Okay.
Axel, go ahead.
If you have a bit more time, two questions. One is very technical, and the other is very applied. The very technical question is: I would try to solve these problems by eliminating the resources, and then I get an effective competition matrix for the consumers. And is there any if in your kind of setup does the competition matrix have a particular structure of sorts?
Yes. I cannot. I'm not sure how to describe it, but yes, it has a particular structure in the sense that you don't see. It depends in what setting. So if you consider the setting where this epsilon is different from 0, so you have the perfect trade-off. These are the species that survive, right? So basically, the competition matrix is these times the transpose. If you have if the trade-off is not tight, then the structure is way more complicated. And because not all the species survive, you select some, and I don't have a clear a clear answer to that.
Okay. The other question, the super applied question is: you showed us some images of the outcomes, and it's kind of alluded to microbial ecology and the idea of the traits are more important than the species.
Yeah.
How far does the match with observations go, really?
You mean the observation or the
yeah, in microbial communities, there's data for microbial
I think it's something that, personally, I think that it's a very, the idea of functional redundancy, etc., is something that it's very, or it was, I don't know, very popular, but it's not something where there is a clear, I mean, there are hints, but it's not really obvious or clear what is the evidence for that. In the sense that it's not something that is easy and it's not obvious what it means to test it.
Okay.
In the sense that even if you, I mean, let's say there are functions or traits that are constant just because, I mean, they're constant even if you take some species at random, right? Because if you just take like many species at random, they just represent what is the average trait, right? And the fact that this is robust is not because you have really a dynamics that force this functional composition to be. So
okay.
I think that, let's say, there is on the experimental side, there is work to be done. I think on the other end, I think that it in some sense is the right variable. That, for instance, with this microbial species, we probably don't care about the identity of all this population. Right? We really care about what is occurring in the community.
Yes, thank you. Thank you very much.
Yeah, thank you.
I like your presentation. Thanks.
Thanks a lot. Are there any final questions? Looks like we're all out. So
Okay.
thank you very much, Jacopo, again. It's really,
Thanks a
really
lot
interesting. And
thanks a lot for the question and the invitation.
no, absolutely. It's fantastic. Thank you.
Thank you.